Assalamualaikum and good day everybody. Welcome to another video on engineering analysis. And in today's video, we will discuss the basics of elements in FEA. This is an important topic regarding the types of elements and their appropriate application in solving an engineering stress problem. I hope you can join until the end of this video. For today's learning objectives, the first one is to how we determine elements in the context of FEA. The next one is we are going to define what are the types of fundamental elements in FEA. And the third one, we are going to identify the appropriate application of the elements in an engineering problem. You need to remember that FEA is just a tool. It can calculate stress, displacements and such, but it cannot make decisions on whether the results are accurate or even whether the part fails or not. FEA is only effective as the knowledge and experience of the user. Now moving on, in this slide, we will discuss what are FEA elements. FEA is governed by mathematics in FEM. If you remembered in the last video that I mentioned about FEM being the math behind FEA. FEM solves stress and strain in the material by subdividing or meshing the part into smaller elements or mesh. This is similar to the concept of digital images where the image is constructed of millions of small pixels. You can say that the pixels in the image are the elements of the image. Hence, the lower the resolution, the blockier the image will look. Calculation is done on these elements and then the results are reassembled back to represent the overall part. By subdivision, it is easier for the computer to calculate the results for one element and then reassemble them afterwards to produce an overall result for the whole part. But this is easier depending on the element count. The fewer the elements, the easier the computation, but the less accurate result you will get. The process is executed in the background in FEA. This makes FEA software nowadays more user-friendly and reduces the need of the user to learn high-level mathematics to use the technology. The following diagram illustrates the FEA process for a typical linear static analysis. We start with our CAD, where our CAD contains geometrical information regarding the part to be analyzed. Here we would determine the appropriate element type that can capture the part geometry as close as possible. The next step is to assign the material to the elements of the part. This will add information such as material density, Young's modulus, and the Poisson's ratio, so the solver knows how the material should behave in our simulation. Here is where the simulation accuracy and realism increases. The next step is the meshing process. Here is where we are going to subdivide our model into smaller elements that we have predefined in the first step, whether we are going to use 1D, 2D or 3D elements. Here we will determine how many elements that we want that will give an acceptable accuracy while not overloading the computer's resources. Then we move on to the boundary condition. This is where we define the position, the direction and magnitude of the force. We also define the location and type of constraints for our model. Then the completed analysis setup is then sent over to the solver, where the FEM computation will begin. Finally, after the solver has finished computation, we can use the post-processing tools which are available in FEA softwares to view the stress and displacement results. As we can see from the process, most of the complex computation is done by the FEA software, but the input to the model setup requires the user to make intelligent decisions to ensure the results are as expected. Now we move on to the element types in FEA. As you can see in the illustration, there are three fundamental element types in FEA. The first one is the 1D beam element. This is usually used to analyze parts that are long and slender, like a hollow steel section. The 1D element comprises of two nodes and one line. The second one is the 2D shell elements. This is usually used to model geometry that has constant thickness throughout. For example, sheet metal and injection molded parts. The third one is the 3D hex or brick element. This is used to model geometry that has a comparable dimension in all ranges of X, Y, and Z. We will use these three element types to model most of the man-made objects. So make sure you are familiar with these three elements, as it will provide you with a strong foundation in FEA. Now in the next slide, we can see the elements used in the simulation of various cases. In the first case is structure analysis. This is the best situation to apply 1D beam elements to represent structures. As you can see here, there is a house structure that is made out of beams. The next is a space frame for a race car. The next case is where 2D shell elements are used. Here we can see the beverage can is undergoing a crash test. Here the 2D shell element best represents the thin sheet metal of the can. The next case is a custom steel structure made out of steel plates. Then we move on to the last case where we can see 3D hex elements being used to represent a piston and a human heart. As the case for the human heart, we can see from the cross-section here that if we had used 2D elements to represent the wall of the heart, we would not capture the difference in the thickness of the wall of the heart. This was the deciding factor as to why 3D elements were used instead of 2D in this heart case problem. So, to sum up the application of elements, if the problem deals with hollow structures, concrete beams, or anything long and slender, it is advisable to use 1D beam elements. If the problem involves thin or geometries that have constant thinness throughout, then use 2D shell elements, as this best represents the geometry. Example like injection molded parts and sheet metal or plate parts. Finally, if the simulation involves 3D parts, for example, machine parts or casting parts, then this geometry is best represented by 3D elements. As a final conclusion, we can say that FEA elements are created by subdividing the whole part into small elements, where this process is called meshing. There are three fundamental element types, which are 1D beam, 2D shell elements and 3D hex elements. Each of the element types is used according to the specific shape of the geometry that is to be analyzed. 1D are best suited for long and slender geometries, 2D elements are for wide and thin geometries, and 3D elements are for geometries that have comparable depth, width, and height dimensions. You must remember that these are best practices followed by the industry. And as all guidelines, if you understand the rules, some rules can be bent. For example, the hard analysis case, where they used 3D elements instead of 2D. Thank you for joining me. I hope this video will help you understand the basic concept of finite elements, what they are, how many types are there, and how they are used in solving engineering problems. I encourage you to find more information regarding this on the internet. Please leave your questions and comments in our Google Classroom. Until the next video, Assalamualaikum and thank you.